Okay, well, I guess we'll see if other people join in a minute. Welcome to our first seminar of June. It's hard to believe that it's June already. We're going to have two very good talks today by Alun Lloyd and Amanda Randles, and perhaps some interesting discussion afterwards. I need to remind you that the meeting is live streamed on YouTube and is being recorded, and that those recordings will be archivally available. And I encourage you all to help us make those recordings known and ensure that they receive the attention that they deserve. As always, myself, James Glazier, Reinhard Laubenbacher, Jim Sluka, and Bruce Shapiro are available to do our best to help out with any suggestions or issues that you may face. And look forward to working with you to make these meetings as productive as possible. We have our usual set of communication channels and encourage people to help us distribute them. In particular, as I mentioned, the YouTube recordings I think are quite a valuable resource. There is an IMAG LinkedIn page, and there's a Twitter and Slack channels. If anybody has requests for those or needs access, please talk to Jim Sluka. He's the expert on the web connectivity issues. Then I don't want to take too much time. Are there any announcements that anyone would like to make? Any short announcements? I guess the big news that everybody is aware of, and we're only very peripherally connected to, is that this big NIH initiative, Bridge to AI, and the fact that they're going to be having a series of workshops starting next week on that. I don't know if anybody in the room actually is a core participant of that, and maybe could tell us a few words about it. If there's somebody here who knows about it and is willing to speak for a few seconds, that would be appreciated. If not, it's fine. We'll all find out next week, I guess. But that looks like a major initiative that could potentially have very significant effects on what we're trying to do here. Any other comments, announcements? No. Okay, next week we have Charles Taylor from HeartFlow and Addie Stern, who's going to be talking about viral sequencing and SARS-CoV-2. And he said he might also be talking a bit about breakthrough and the efficacy of vaccines, which would be very interesting. June 17th, we have Chantal speaking. We still have an open slot for the 17th, so if anybody would like to volunteer themselves or suggest somebody who'd like to speak on the 17th, we would appreciate it. June 24th, we have a major talk by Lisbeth Garris, who's leading the latest incarnation of the Virtual Physiological Human Project. It's something that we all need to be aware of and should coordinate with. And then Rufus Pollock on data management. As always, we would appreciate your suggestions for future speakers. If you've already spoken in the group and you want to speak again, let us know. There's no rule that says you can't speak more than once. If I can ask people who are not speaking to mute themselves, that would be kind of you to reduce background noise. We will, as usual, go through both talks before we go to questions to make sure that we have plenty of time to get both speakers through. It's always hard to get through in 15 to 20 minutes for a talk. And so we appreciate our speakers cutting down their material to the bone so that we can have time to hear from both of you. And I'll typically break in with a 5-minute warning just to keep people on schedule. To begin with, we'll hear from Alun Lloyd on bidirectional contact tracing for COVID. As people know, I don't typically do an elaborate introduction, and I will turn it over to Alun.
Very good, thank you. Okay, so hopefully my screen sharing is working. So yeah, I'm going to talk about contact tracing. And so this project was initiated by Kevin Esfeld, who's at MIT. And the majority of the heavy lifting on the simulations and the day-to-day work on the project was done by Will Bradshaw, the first author of the paper I'll mention at the end. We had funding from a number of places, including the Open Philanthropy Project and the CDC. So forward contact tracing is a sort of commonly used approach to try and limit and control an outbreak of an infection. So this is contact tracing is most effective during the early stages of an outbreak. And the traditional approach is what we call forward contact tracing, that says if you've identified a case, you try to find and then isolate contacts who they may have infected. And of course, there are issues with doing contact tracing in reality. Finding all the contacts of someone, you have to find them quickly enough in order to isolate them before they go on and cause secondary infections themselves. And one question you might wonder is whether you should test and confirm that someone actually has the infection before you do tracing, or before you do tracing. So one of the questions that came up early in the COVID outbreak, and this idea had been out there for a while beforehand, is whether digital approaches, so use of cell phones can help. So there are some quite specific difficulties doing contact tracing with the SARS-2 coronavirus, largely because we have asymptomatic cases. So there are people who are never going to present themselves as cases to a contact tracing system, and also because you have pre-symptomatic transmission. So by the time you found a case, they've already, at least by symptoms, they've already caused, potentially caused a number of secondary infections. So partly with the digital contact tracing in mind, our project set out to ask about what we call bidirectional contact tracing. And that not only tries to figure out who you infect, but also the person who infected you. And the way you can achieve that is under the standard contact tracing guidelines. People ask about contacts starting from 2 days before symptoms started. If you instead ask about contacts starting from 7 days before symptoms, you have an increased chance in being able to trace backwards from a case and find the person who infected that case. Of course, the flip side of this is that because you're asking people about their contacts over a longer period of time, you end up hauling more people in your contact tracing net. So there's a lot more work involved with that with the bidirectional contact tracing than the forward contact tracing. Also, of course, because you're asking people to recall their contacts, it might be that people have a better memory for recent contacts and a poorer memory the longer back you ask about contacts. And so the approach we used was to take an already existing model of what was already a model for forward contact tracing, was in the literature, that was from the London School group that came out early during the outbreak, so Helliwell et al. And this is a branching process model for transmission. So this model models transmission events rather than contacts, rather than just contacts. So it models successful transmissions rather than all contacts that a person had, but it generates a transmission tree starting with an index individual. And we took this and modified it to allow for both forward and backward contact tracing. Now, it turns out that when you model contact tracing, when you do contact tracing, timing is absolutely crucial. So you have to model lots of different distributions of time intervals in this process. So, for example, the incubation period between someone becoming infected and showing symptoms, the serial interval, that's the delay between someone becoming infected and causing a secondary infection, and then also things like testing delays, the time it takes someone to be identified as being symptomatic and then get isolated. So in this branching process framework, we can ask questions such as the percentage of outbreaks that we introduce in a simulation that get controlled, successfully controlled, get curtailed, given different probabilities of being able to trace a contact. And so we use that measure, and we also look in the transmission tree at the average number of secondary infections and how that depends on various features of the contact tracing process. And implementing the standard contact tracing guidelines with a baseline R0 of 2.5, we see that manual tracing will typically fail to control an outbreak. But if we do this bidirectional tracing, so we extend the trace limit from 2 days before symptoms to 7 days before symptoms, and allow looking at both forward and backward contacts, we get an improvement. So we sort of double or more our chance of controlling an outbreak, and we cause a substantially larger reduction in the mean effective reproduction. It turns out if we just looked at digital contact tracing, the performance there would be highly sensitive to the fraction of the population who have the smartphone app and who choose to share their information. And one of the reasons behind that, in this framework at least, is that if you want to be able to trace a contact using a digital approach, using the cell phone app, both the person who's infectious and the person who becomes infected by them has to have that cell phone app for this to work. So there's a quadratic dependence here on the adoption of the cell phone app. But we found that if you hybridize and you use both manual contact tracing and the digital contact tracing, you significantly improve performance, even when the adoption of the digital app is not all that high. So now, even when we have maybe only half of the population or below using the smartphone app, we can get the effective reproduction number down close to 1. And I should say that I guess here we're not considering other reductions in transmission, such as mask wearing or social distancing. So, so I wanted to mention this paper came out in Nature a few weeks ago. So the UK had a nationwide rollout of one of these cell phone apps through the National Health Service. And I guess it had a slightly rocky initial rollout, but over time they made some improvements and so on. And they said that in the end, although I guess this is towards the end of 2020, they were finding roughly a quarter of the UK population was using this cell phone app. And they found that use of the app, depending on the assumptions they made, reduced the number of cases by between 100,000 and 900,000 cases. So that actually, it turns out that's a much larger impact than we would have predicted under our branching process model. And I could talk later about why that might be the case. So, as I said, the pre-symptomatic transmission and the asymptomatic transmission makes control using contact tracing challenging for COVID-19. At least in our model, the digital approaches aren't a silver bullet unless there's very high adoption and use. Bidirectional approaches can greatly increase the effectiveness of contact tracing. And I can talk a bit about why that might be the case. And I should say that there are some countries that did either deliberately or accidentally implement bidirectional contact tracing in their approach. So in Japan, they did cluster analysis, which would try to identify the source of the analysis, or of a cluster rather, an outbreak cluster. So they were going both forwards and also backwards. And it was found that contact tracing was highly successful there in reducing outbreaks. And one of the reasons I haven't talked too much about all the assumptions in the model, because I want to try and keep this short. One of the things that we have in the branching process model is heterogeneity in transmission. So there are superspreaders, the secondary infection distribution. The number of secondary infections is negative binomially distributed. And so most individuals give rise to few secondary infections. A few individuals give rise to lots of secondary infections. So if you think about it, those super spreaders are disproportionately represented in the population of people who cause individuals to get infected. And so by backward tracing, you're more likely to find a super spreader than you are to find like a typical member of the population. As I mentioned before, using other approaches, even mildly effective ones, are going to sort of add on to the impact of contact tracing. So will help that effective reproduction number come below 1. And this work, that's right. So there's a medRxiv preprint freely available. I guess this work was actually done a year ago now. Again, it's hard to believe that was a year ago. And it appeared in Nature Communications back at the start of this year. And I have another couple of slides, but I think I'll leave them in case we want them for the discussion later on.
Well, we have time. We actually got through that in record time. So
okay. Well, you said 10 minutes, so I took that literally. Okay, so, okay, well, I've got my 2 other slides then. So my reverse, as I said, the reverse contact tracing is made more effective when we have this heterogeneity in transmission. So as I mentioned, these super spreaders or super shedders. So some individuals cause lots of secondary infections. And if you trace forward, you typically will find a typical individual who will have few secondary infections, but because they cause more infections than average, those super spreaders are overrepresented in the population of people who caused infections. So backwards contact tracing is more likely to find a super shedder than a typical infected individual. And the other thing to mention here, this is actually really quite an important point in terms of the modeling. As I said, we used a branching process model, which is a sort of a commonly used framework in this sort of analysis. So it's a sort of framework that mathematicians like, in part because it's quite amenable for analysis. So we can ask things like outbreak probability, we can do R0 calculations. But as I said, the branching process is formulated in terms of transmission events rather than contacts. And so it's much more difficult. Well, we can make some additional assumptions, but it's more difficult on the face of it to calculate what I call the collateral damage of tracing. So the idea of contact tracing is that you isolate risky contacts. And so one of the criticisms of contact tracing approaches in anything other than the very earliest stages of an outbreak is that you can end up isolating so many people that, well, presuming that you can find all those contacts sufficiently quickly, you can quite easily end up isolating sufficiently many people who aren't infected, that you're basically doing a local lockdown. So, and of course, really you want to be able to do a sort of a full analysis of how many people are you isolating, what's your capacity to trace all those contacts and so on, because those are clearly important on the ground issues. Also, the branching process model has a very simplified description of how the transmission process works. It basically treats all individuals as coming from a single pot albeit a heterogeneous part of secondary infection causes, it doesn't capture sort of the many important aspects of social structure. So, we don't have households, workplaces, school-based transmission. We don't have any local spatial structure. So there's a lot more independence between events in a branching process model than there would be in a full individual-based model that had that social structure. And so it very likely represents a worst-case scenario. So the UK group, the British group that did that study that appeared in Nature, their simulations are based on what they call a realistic social structured individual-based model. And they point out that there's a lot of overlap in sort of clique structure and overlap between, if I have a contact, some of my contacts will share contacts with those people. And that, it turns out, makes some of these, makes that digital approach more effective, because you don't have to worry quite so much about the level of coverage in that case. On the other hand, trying to communicate the results of models, branching process models make fewer assumptions, and those assumptions are much more transparent. So, it's one of the big problems of the big individual-based models, that it's very difficult to communicate all of the assumptions that go in there, and it's difficult for someone else to reproduce that analysis independently without going through a long and painful process of recreating an individual-based model yourself. Okay, I am going to finish there.
Okay, thank you very much for a lovely talk. So we'll move on, and our second brief talk is by Amanda Randles, who is going to be talking about personalized flow simulations. And I will turn it over to you, Amanda.
Okay, so hopefully, yeah, you guys can all see this. I will say, just as a primer, if you have any issues hearing me, or there's something, we are having a pretty severe thunderstorm at the moment. So you may end up hearing a lot of noise in the background. So how I set this up today was just kind of to give you an overview of how we're using 3D blood flow simulations, how we're using, the idea of personalized flow simulations in a few different instances. And I have just two case examples kind of called out. And kind of what I'm really excited about is using physics-based models kind of paired with large-scale parallel computing to answer questions that wouldn't otherwise be tractable. So a lot of my background is really focused on, developing codes for large-scale supercomputers, and now we're trying to bring those to personalized medicine, personalized blood flow simulations, and then I'll touch a little bit on another use case where we're looking at ventilator splitting. It's a bit more relevant to a lot of the talks you guys have been having in these seminars on the COVID side of things. So one of the cases that my lab is really excited about is the potential for using personalized fluid simulations. And a lot of this is tied into that imaging, what you're getting from to make it patient-specific model, simulate the flow in 3 dimensions, and try to really understand that patient's underlying hemodynamics. So what you're seeing here is a personalized blood flow simulation for the coronary arteries specifically. This is actually a few years old at this stage, but it gives you a really good idea of what I mean when I'm saying, when we're looking at these personalized 3D flow simulations. So we're getting data from medical imaging like CT, MRI scans. We're reconstructing that 3D topology of the vasculature, and then we're running these flow simulations in that geometry. We can also take into account interactions with the individual cells. So that's what you're seeing here, all the individual red blood cells. In this model, we have about 200 to 300 million different red blood cells interacting with each other, interacting with the fluid. And you can kind of understand why this ends up starting to be so computationally complex. Conventionally, we've used a lot of these types of models to look at peripheral arterial disease, coronary artery disease, but we are branching out now and starting to do a few projects looking into cancer metastasis and trying to understand what it is about different circulating tumor cells that make them move through the body at different stages. So when you're thinking of this video, kind of imagine, in vessels in the body, dropping in a cancer cell and watching it interact with the red blood cells with the endothelium and kind of moving around and being able to track that movement of that cancer cell. And again, this all comes back to the requirement for using large-scale parallel computing to try to address the computational components it met by these challenges. So just to give the overview of the kind of, the setup of what we're doing, we're using, patient-derived imaging. So we're using CT scans, MRI scans, and some of our work, we use 2 biplane angiograms, and then we're using them from the different angles and reconstructing the 3D geometry. But basically, anything you can do to get that 3-dimensional topology for that patient's vasculature. We use conventional software. We typically will use Mimics from Materialize to segment the data when we're working with CT or MRI scans. But we end up pulling out a triangulated mesh file representing the 3D geometry of that patient's vessels. And that's what you're seeing in the top right corner of the image here. So once we have that 3D mesh file, we use a computational fluid dynamics approach that is similar to what you typically see if you've taken fluid dynamics classes. You've been introduced to the idea of Navier-Stokes. We're using lattice-Boltzmann, which is an alternative to solving the Navier-Stokes equations. The useful thing to know about the equation is just that it's taking a discretized approach to the velocity or to the fluid calculations. So basically, we're filling that 3D triangulated mesh with a regular Cartesian grid. We're identifying what grid points are inside the mesh, what are outside the mesh, what are the inlets, the outlets, the wall nodes, and then we're solving these fluid dynamics equations at each of these grid points. To do this accurately, it requires very high resolution. So then that leads to this idea of requiring large-scale supercomputers. So a lot of the work we're focused on and we think about is how do we scale this? How do we run it efficiently? And what needs to go into those models? You can kind of think of these large-scale models. One way of using them is to try to throw everything into the model that we can, and then identify what we can then backtrack out and either make patient average, not have to directly measure certain parameters from the patient data, or what parameters can we remove depending on what kind of method what you're actually trying to measure. I won't get into it in this talk, but I'm happy in the discussion to go into it a bit further. But we have done a lot of work to try to validate the model, and obviously, anytime you're looking at the computational models, kind of think about why should you trust this. And then again, I won't touch on it as much here, but for the discussion, we're also very interested in thinking about how do you interact with this data? How do we make it usable to the clinicians, to other researchers? We're very active with looking at ideas of immersion and the level of immersion for interacting with this data. So how to use virtual reality and augmented reality to help improve your surgical treatment planning and kind of guide these simulations, along with even just what's the best representation to give the data back to the doctor so they can use it accurately and most efficiently. So, representing it like a 2D map like you're seeing here, or a 3D map below, or what color scale to use and questions like that. I wanted to put this up just to kind of give a broad overview of the types of ways that we use personalized flow simulations. You often see it for diagnostics, for non-invasively trying to identify different hemodynamic parameters. One of the things our lab has done is really push the level of, by using these large-scale supercomputers, push the amount of vasculature that can be run, that can be simulated. So we can now simulate flow, bulk fluid flow in the full arterial geometry. So we can start asking questions about peripheral arterial disease. We can look at ankle brachial index, but we can also look at the different local changes in the hemodynamics. So if you were to place a stent, if you have a coarctation, if you have a small change or a stenosis occur in a different region, instead of just looking at the local hemodynamics, we can now ask questions about, how does that affect the ankle brachial index, or how does that affect more global quantities for that patient. These models are very useful for treatment planning. So we have a lot of work trying to understand, before the doctor ever goes into the operating room, can you virtually, simulate what different treatment options are for that specific patient? So the picture you're seeing here is for pediatric cardiology. We're looking at patients with hypoplastic left heart syndrome. So they have, only one ventricle in their heart is really working. When they're born, they need to shunt the blood and kind of circumvent this non-working ventricle. So there are a few different surgical options they can use. So they can put in a shunt, they can put in the MBTA versus there's different options of the shunts that they're going to put in. And we can simulate not only those specific types of shunts, but the angle of the shunt, the geometry of that shunt, what diameter should it be, and try that before the doctor ever goes to the operating room, see what that best option is for the treatment planning for that specific patient. So it's a strong use case for these large scale computational models. And then on the other hand, we are really looking at fluid structure interaction, trying to understand more of the basic science side of what is it about these different cells that cause them to move in different locations. What are their interactions? We have adhesion models built into these types of computational setup to understand, how does a cancer cell interact with the endothelium on a receptor ligand basis. So down to the nanometer scale of looking at the individual ligand receptor pairings. So we can kind of span from the bulk fluid at the full body, trying to understand how different treatment mechanisms or different treatment options are going to influence different local quantities, down to this basic science question of, what is it about a lung cancer cell that's going to cause it to metastasize to a certain region? I just put this in as a throwaway if people are interested in talking about later. To do this, a lot of the work really does rely on strong computational component. I think some people in this group are interested in the parallel computing side. We've spent a lot of time in my lab collaborating with the Department of Energy labs, trying to figure out how do we really scale this code efficiently. The image that you're seeing here is a graph of when we were scaling on all of the Sequoia system that used to be at Livermore, and that was 1.6 million processors. We're now preparing the code to run on Aurora. That'll be the first exascale system at Argonne. And we're really focused on, it's not just how do we run these models on a desktop or on a laptop or something on that level, but really trying to see how can we really push this and use cutting edge technology to see how much of the system we can model and how far we can go in that direction. We're also currently investigating a lot of options in the cloud if people are interested in that side, where I think an easy question here is if we really want this to be translatable and usable in the clinic, the hospital is not going to have access to a DOE scale supercomputer. So how do we make, how do we push the research side, but then also make something that is translatable and usable in the clinic? And how do we kind of push that front? And to that end, we're looking at machine learning based models. We're looking at how to speed this up and how to embrace different cloud-based architectures. It sounds like you'll hear more about this next week, so I won't touch on it as much, but this is very similar to what you'll see with the heart flow discussion. But one of the key examples that people are using right now for the role of 3D blood flow simulation is looking at this quantity of fractional flow reserve. So it's that pressure gradient across a narrowing or stenosis in the artery. And they use this to determine should they or should they not place a stent. So if that fractional flow reserve is above or below 0.8 in the hyperemic condition, they'll decide that'll guide whether or not they place a stent. And what we're seeing now is the opportunity to use non-invasive imaging to run a simulation, extract this quantity, and use that simulation-based metric to determine should you or should you not place a stent, and not have to do an invasive procedure, place the patient under hyperemic state, use a guide wire invasively to measure it. And we're starting to see FDA approved, like heart flow, which you'll hear from, I guess, next week. We're starting to see technology to allow this where we can use personalized flow simulations for this. I kind of wanted to keep skipping through, so I don't take too much time, but we as I mentioned, we're using these kinds of models for treatment planning. So, when you're looking at something like a coarctation of the aorta, you could do angioplasty where you're placing the balloon, you can place a stent, you can do anastomosis where you're going to just remove that stenosis. And one of the things we're working on is, trying to create virtual simulations of all the different treatment options, as is also something we're doing hand in hand with the virtual reality component. So we have an immersive way for the doctor to try different surgeries, different treatment options, and see how that would influence the hemodynamics using these virtual simulations. We are also pairing this work with machine learning, which I think might also be of interest to this group of, when you're thinking about these flow simulations, it's not just, running an exercise state or running a rest state. We want to understand the entire, what if that patient is at high altitude and running? What if they're in Denver and running? What if they become pregnant? What if, they're anemic? There are many, a wide variety of conditions you really want to take into account that may not be able to be captured in the doctor's office. but it's also not tractable to run a flow simulation for each of those different conditions for each patient that comes in. So what we've identified is a way of using machine learning kind of in pairing with a design of experiment approach to identify the minimal number of simulations you need to do for a new patient to then be able to project and predict the entire landscape of all of the different parameters, situations that they may have, and do a risk analysis for that patient with the minimal number of compute hours being used. This is kind of giving you that picture of that landscape. I can go into this more in the discussions if people are interested. I want to make sure I touch on fluid structure interaction and get to the ventilator work. And I wanted to just kind of mention, I've shown a little bit of the bulk fluid models. We're also very interested in how do you integrate fluid structure interaction. So looking at red blood cell movement, doing that accurately, integrating a cancer cell, and trying to take into account the cancer cell movement or specific cell movement over a long trajectory. So in this group, you may be more interested in movement of white blood cells or neutrophils or platelets, but you can kind of use the same kinds of models to capture adhesion, to capture interactions with different cells, and do that over long periods of time. And that's one of the things we've been developing is this adaptive physics model where we have essentially a moving window that tracks the cell of interest. And inside the window, you have all of the fluid structure interaction. Outside of the window, you just have the bulk fluid model. So you're getting that cellular resolution and the cellular interactions, but you're able to track the model over much longer distances than you would normally have been able to. And then I'll just give a really, really quick version of the role of the ventilator splitting. And I think I just wanted to touch on this use case quickly because it is more timely and kind of related to all the talks you've been having on the COVID side. And I don't think I need to do much of a setup and information and background on this, but I'm sure you all remember last year when initially one of the big issues with the ventilator shortage. There was a team at Duke that created a way of splitting a ventilator between two patients, which would allow you to double the efficacy of these ventilators immediately. And the key part was they were able to tune the ventilator so that tune the splitter so that it could split the ventilator between two patients that didn't have to be matched. So they didn't have to be matched in terms of lung compliance or weight, which made it much easier for the physicians. The problem they had was that they wanted to be able to give the doctors a way of identifying what's the best way to tune this to tune it for two different random patient pairings that were going to come up. And they came to us and asked if we could create a personalized fluid simulation that would simulate how the ventilator pairing would split between these two patients and calculate, delivered tidal volume, PIP, PEEP, and try to optimize, basically tell the physician immediately what's the best and optimal setup and what resistor should you be using to split this ventilator between any two patients that you may come across that you need. I won't go into a lot of the details, but the interesting parts that came out of it, it ended up being, we were able to do this with a one-dimensional model, which made it much more computationally straightforward. But as you can imagine, in order to put this forward for FDA emergency use, we wanted to have all of the data available. We didn't want, when it goes on the floor for the doctors to have to wait for a simulation. So we ended up wanting to do a brute force simulation of all of the different potential pairings that you might have. And what you're seeing here on the right is, the ideal of, what the end product of what the app is that we provide to the doctors, of the information they can put in and the information they want out. But it gives you a sense of the different parameters that we may get. And then, if you're putting in patient weight, we want, every weight for, every 2 kilograms, and see, if the patient is 100 kilograms to 102, 104, you can kind of imagine how the number of parameters is going to explode very quickly and require many, many simulations. And I think that kind of the biggest takeaway from doing this work was when I'm sure you guys are familiar with the HPC consortium that came together last year. We submitted a proposal to that consortium, and it was very science driven, where we told them, we didn't ask for the type of technology. We didn't say anything about the hardware, what we wanted to run on. We just told them the problem we had, how we needed to solve it, what code what the code base was, what the language was, and they paired us with Microsoft Azure. And the interesting piece is we submitted the proposal on Monday. We were paired with Microsoft by Thursday. We had our first meeting with them Thursday afternoon. And by that following Monday, we had run about 800,000 compute hours to complete all of the simulations we needed within 1 week of submitting the proposal. So I think it's just worth kind of thinking about that and keeping that in mind, of having the science-driven proposals and the way people kind of came together to allow us to complete that number and that sheer amount of simulation, and that kind of turnaround is pretty amazing. And I'm happy to talk about that further in the discussion as well. So I'll wrap up there, and I know I'm kind of pushing on time, so I'll stop there.
Well, two very impressive talks. Thank you very much. Both of you got through very quickly, so we have plenty of time for discussion. Do people feel that you'd like to have a split room, or shall we have a joint session? Reinhardt?
Well, I think we could start out maybe with a joint session and see how it goes.
Okay. I can create breakout rooms at any time if people want to delve in deeper. So we have gotten through very quickly with two very impressive talks. So I'll open the floor for questions.
I'd be happy to ask one of Amanda. Thanks for a very stimulating talk. You alluded to ways that you validate. Could you tell us a little bit more about how you validate your models?
Yeah, that's obviously very important. So initially, we did a lot of work with David Frakes' lab when he was at Arizona State, so that we started with trying to validate just the bulk fluid side. So we 3D printed the topologies that we got out of the segmentation. So we 3D printed rigid wall geometries, ran particle image velocimetry experiments. So it was a very controlled experiment where we know all of the settings, and extracted velocity profiles using particle image velocimetry. We did this starting with the aorta because it had closer to turbulent flow. We figured that would be the hardest. If that worked, everything else might fall into place and be easier. So we did particle image velocimetry for the aorta, the femoral geometry, a coronary, just like different length scales, and trying to make sure we're really capturing flow properties correctly. We've also done this at the microvasculature scale with Lawrence Livermore National Lab. And in that setting, we did this where they were bioprinting geometries, similarly doing PIV, so the particle image velocimetry, but they also were, they made endothelialized channels. So it wasn't just rigid walls. So we had that side. And then we've recently completed about a 200 patient trial with the FFR side, where we are comparing against the measured value invasively with the guide wire for the pressure gradient across the stenosis to what we're getting out of the simulations. So we have kind of both the invasive measurements for those, like the single metric of the FFR, but then we've really relied on the particle image velocimetry inside for things like that to get the full, ensure that we're getting the full like velocity profile in the 3D space correct.
I'm guessing the particle how do you pronounce it? The particle tracking is not actually simulating the blood cells. Is there a level at which you're validating and sort of distribution of blood cells in the flows?
Yeah, so I should have commented on that too. So we are doing a lot of work for fluid structure interaction. It's interesting. We've kind of gone the other direction where we've started validating that we get the right cell movement for one cell. So we've actually been replicating single cell experiments. So like with red blood cells, doing like the optical tweezers, some inertial confinement. And for different cancer cell lines, it's been putting, we've been working with Scott Manalis's data from up at MIT, where he has devices where it's basically passage, like constriction through passages of different cancer cell lines. And we're simulating that specific cancer cell moving through a microfluidic device and seeing if we're getting the right passage times, if we're mimicking the right mechanical behavior of those cells. And then trying to determine what do you need, for the cancer cells, do you need a cytoskeleton model? Like what complexity of the model do you need to capture those behaviors? And then once we have like the single cells, then we're scaling up to the large cell. We haven't actually completed any validations at the large scale side with many, with hundreds of millions of cells to ensure that we're getting the right flow split or, the right density in different areas at this stage. That'd probably be a really good next step to make sure that as you're scaling up, you're getting the right behavior. We've just completed the single cell validations and we have the capabilities to scale up. So they were kind of primed to do those kinds of studies, but that would probably be the next step of making sure we trust everything.
Okay, I see a hand up under Amanda's, although it's clearly not an Amanda speaking, so go ahead, please.
Hi. Yeah, so I had two associated but pretty simple questions. I come from a simulational background as well, and I'm very interested. You mentioned that you have the red blood cells that interact with each other and the arterial walls or the blood vessel walls. So could you briefly describe what specifically those interactions are? Are they like, hard disk or Leonard Jones potentials, or how exactly are you modeling the collisions of these things with each other?
So for us, we're using immersed boundary as the main fluid structure. So we have finite element models of the cells. We do have, in like 99% of our work, it's rigid. We're in the process of adding deformable walls, but the cells are deformable. So the cells, which is an interesting, So the cells are all using finite element modeling with immersed boundary to couple with the fluid side. So you're using that as your interactions. But then it's the lattice Boltzmann side of having a rigid wall with bounce back on the vascular walls themselves.
Okay, well, that answers my second question, because my second question was going to be if either of the dynamics are deformable or not.
Yeah, it's kind of interesting. To answer a lot of the questions we've had on the clinical side, you don't necessarily need the deformability taken into account in the walls of the vasculature. But we're starting to look at questions where that, when you're looking at something like aortic dissection, you really need to have mechanical properties. So there are certain diseases where you really do need that. And so we're now moving over to have the deformable walls, but it's very similar to the deformable cell setup. But I see it shouldn't be, it should be a straightforward jump, but we're not there yet.
All right. Thank you.
Okay, Lorenzo, I think you were next.
Hi. I have one for Amanda. Well, first of all, thank you both for the amazing talk. And Amanda, you talk a lot about essentially big vessels, right? So most of the assumptions are in big vessels. So I was wondering if you looked at, or you're thinking to look at microvasculature for a few reasons. One of these is that the geometry in different tissues is very different, and is probably fascinating to think how this emerges. And this links to the next reason, that is, we have probably for sure we have questions in vascular biology where we think it is the flow while we develop blood vessels that differential flow dictates what shape certain vessel will take, or if there are other cues which dictate the shape, and then they will on the other side influence the flow that affect the flow that goes into the vessels. So have you looked at microvasculature or thinking to do like that? So
we have, but probably not as, I think you could do a lot more. We've started looking at microvasculature because right now we're trying to understand circulating tumor cell movements. We're trying to get not the tumor itself, but once the cancer cell has moved off the tumor and is in the vasculature. So in that case, we really do care about the microvasculature. But at this stage, we've really focused on making sure we have the cancer cell model itself correct. So we haven't been doing anything we've been validating our adhesion model. So we have a little bit of a microvasculature in our adhesion models, but it's more of the construct to see how are the patterns of adhesion changing the motion. We've been kind of limited. We've done some work with, I had mentioned Lawrence Livermore National Lab. We are running some flow simulations, some data from Roger Kam's lab. But it's been more proof of concept of can we run flow in the microvasculature regions. We've been limited, and maybe someone here would be able to point us in the right direction. We've been limited in, I don't have a lot of data of I don't have in vivo images of the microvasculature or the right geometries. It's really been from the bioprinting side. But we are very interested in that space. We've done a little bit of work with different bioprinting labs. So I think it's definitely an area of interest, but we just haven't, we haven't gone into it very far. We've only done the initial work of validating it with some PIV and the bioprinting, and focused on just making sure that initial cancer cell is correct.
Okay, thank you very much.
I guess we have some data on a microvascular flow in the liver, experimental. Not a lot, but we could definitely talk offline about that if you're interested.
That would be really interesting.
I guess I'm going to break in. Alun has been kind to stay with us, and I want to make sure that he gets his share of questions. I was going to ask two naive questions before we go on to Alun, which were, you mentioned, of course, that contact tracing is most effective when rates of infection are low.
Yeah.
And I wondered
when the numbers of infected are low.
right.
Yeah.
And so I wondered if you could talk a little bit about how these efficacy, the effectiveness of these methods scales as the fraction of the population infected increases. And then the second question was going to be, how do these pooled diagnostic techniques, for example, sewage analysis, play with the kinds of approaches that you're taking? Because it seems to me that that you're doing, in a sense, some kind of pooling in your analysis, and I wondered how those play together. So one, the effect of incidence rates on the efficacy of the techniques, and then two, how you connect those to pooled diagnostics.
So the the traditional contact tracing is very labor intensive, because you've got to find the people who are symptomatic. They come into a contact tracing system, then someone has to be in touch with them, find their contacts, phone those people. And so that's all rather labor intensive and doesn't scale at all well with a number of infected people. That's one of the reasons why people were so excited about the idea of doing this digitally, because the cell phone systems, although there's issues with privacy and so on, but those can be worked around. Those digital systems scale are scalable with population size in a way that the manual approach, to be honest, simply isn't. So someone at CDC, after seeing my talk back in a year ago, asked me about what I thought about the feasibility of doing this backwards. And if you're asking people over this longer time window, the number of contacts you get reported by in the system is a lot higher. So there's just so much more work for the manual contact tracers to do. So the other question was about these sort of pooled approaches, things like the sewage analysis. So I think that's, in fact, I saw a paper that came out, a preprint came out today in the UK, in Scotland, where they had looked at pooled tracing and how predictive it was of the number of cases in different cities. I think maybe they even looked at plants that covered half of the Scottish population or something incredible. So that's a really quite different sort of approach, because the contact tracing is all based on knowledge about individual infecteds, whereas you're not going to get that, at least initially, from those sorts of pooled approaches. Although it might be a good way of figuring out how to dedicate resources to places where the problem is higher.
Well, I was wondering if you're tracing back, and the number of contacts is very, very large.
Yes.
Whether those kind of pooled approaches might at least be able to rule out some of the people that you have to consider.
That's a good point. Yes. Yeah. And indeed, I think some of the I mean, also some of the digital approaches try to use more information than just purely contact. They try to figure out where you've been and the number of risky contacts that you might have had to increase the chance that you're picking up genuinely infected people rather than false positives.
Thank you very much. I think, is it Mitchell? We'll head next.
Yeah, so I guess it's a question for both Alun and Amanda. So I'll start with you, Alun. In terms of, one of the things that we like to talk about in one of the subgroups here is how to effectively communicate science, given the role of science during the pandemic and how effective communication either did or did not work well, depending on which article you read. So I wanted to get your perspective on when you were looking at bidirectional contact tracing, what was your interaction like with the public and the media with these ideas, and how did you navigate that territory?
Yeah, so I to be honest, our paper was rather theoretical, and so we weren't able to make. I don't think we were able to make those sorts of implications that really were direct public facing. But I'll say that the project was actually started because Google and Apple were setting up their protocols for doing the digital contact tracing. And Kevin Esfelt, who started this project, was involved in some of the discussions there. And one of the questions was, how long should those companies be retaining data on contacts? And so part of Kevin's idea in starting this project was to actually get them to extend that window for which they'd retain data. And I know he was in touch, he's been in quite a lot of touch with Apple, Google, and also some states who've been developing their contact tracing apps. He would be better placed to tell you about that sort of public facing aspect than I am, I'm afraid.
Gotcha, thank you. And I guess same thing, Amanda, I know you said you communicated all of your work with getting that funding so quickly. So clearly you had an efficient way of communicating the importance of the modeling to that community. And so I don't know if you could comment on that as well, on how to effectively communicate your science ideas.
Yeah, I guess on that end, it was great in that for the consortium, it was very, it was brought together of people who had a technical background, so that there was that hurdle. It wasn't trying to go broadly to the public. It was people from Microsoft Livermore Labs and that side of things. So that did help a lot on that end. But it is, and that is, it's a big issue of, in general, something we're really focused on, kind of what I mentioned when we're looking at things like the virtual reality, of just the basic question of a lot of the work that we're doing, requires large scale supercomputing, but requires a command line processing and that kind of thing. And that's not what the doctors are going to be doing. So just trying to think of that. Yeah, I guess in general, trying to, distill what is the important part of what we're trying to do and communicate with the, the consumer, whoever it is going to be of interest, whether it's trying to get the, compute time on the, from the consortium side. And that you only had about, I think it was half a page or a page to get across, why is this important? What are we doing? Why do we need to run the simulations? And honestly, when we submitted it, I assumed they were going to come back and give us half the compute time, and we'd have to start paring it down and not just run everything. And it was amazing, and that they were just whatever you need, let us know, and let's go for it. So that that setting was really great, because you did have people who at least knew enough about what we were trying to do to bring, even we had that first meeting with Microsoft, they brought fluid dynamics experts from Microsoft, which I don't even know why they have fluid dynamics experts, but they had the right people in the room, just in case we needed them, to make sure that we were able to hit the ground running. And all of that, just making sure we had an interdisciplinary team ready and there, was a huge part of why we're able to complete everything in just a few days. But yeah, I think in general, we just come back to trying to think of how do we actually, we had an initial paper maybe 10 years ago, just even the basic of what color scale is the best color scale to use to get your data across. It's, I think constantly thinking about communication of the science is very, very important. I think a lot of people here are working, or our physicians are working with physicians. We ran into issues of, people wanted to see the color scale that's in their textbooks and the orientation of the coronary arteries that was in the textbooks, and they did not want to see anything else. And we had to do a lot of, it was kind of an uphill battle to say rainbow color scheme is bad and things like that. So it's very important to kind of think of what is the end goal and what are you trying to do. So yeah, anyway, communication of the results and is incredibly important. It's something I think we all have to think about.
Perfect, thank you both.
John.
I have a question.
Go ahead.
On the contact tracing thing, 2 or 3 times you made reference to a lot of assumptions, and then you moved on. What are some of those things in the assumption list that were maybe the most significant assumptions that you had to make for any of it to make sense?
Yeah, well, as I say, in the framework that we use, the most significant assumption, is just intrinsic in the branching process, in that you assume that each individual is, their number of secondary infections is independent and identically distributed, drawn from some common distribution. So that's just inherent in the branching process formulation. In reality, a real world social network doesn't look anything like that. But on the other hand, my feeling is that many attempts to recreate those real world social networks have deficiencies, and maybe those deficiencies are not always entirely clear. So at least the branching process, the branching process, as I said, has advantages in terms of its transparency, and it's clear what assumptions are being made and what the implications of those assumptions are likely to be in terms of, for example, a branching process is going to overestimate the amount of transmission that happens because you don't have that sort of local spatial structure and clique structure in the social network that we know actually exists.
Is there anything about the biology of the organism itself that is even relevant to a contact tracing activity?
I'm not quite sure what you mean.
Like, how is the organism itself behaving that's causing the infection? The coronavirus itself? Or is that just not relevant to contact tracing activity?
It's not clear to me how relevant it is. I mean, we have sort of descriptions of, the time course of infection, or rather the time course of someone's infection in terms of their infectiousness. We have this sort of implicit description of the fact that people make different numbers of contacts, and so you are just by chance going to have some people giving rise to more secondary infections than others. But it doesn't go much further than that.
Thank you.
I guess, John, you're next, I think.
Great. This is actually a question for Alun. I found your talk very interesting, and actually earlier this year I had an opportunity to help NSF organize some workshops on preparing for and hopefully preventing future pandemics. And part of that was really to try to think about how all the pieces fit together from the parts that John just alluded to on the infectious agent to all the way how the infection spreads in the patient, and even to the epidemiological models. But beyond that, there was also the component of the human behavior, social, behavioral, economic sciences, where I think people are thinking about models. And as someone yourself, I would imagine, who is interfacing both with the patient dynamics as well as the social, when you make a prediction and people read about it, how does that feed back on how they behave? I wonder if you could comment on what you see as the challenges and opportunities in extending your models to human behaviors or policies.
So I think behavior is for sure one of the biggest issues in terms of making like long-term projections of the numbers of cases, because clearly people's behavior changes in response. And so that's actually been one of the criticisms I've had of the way that some model predictions have been discussed in the media. And people will say, oh, well, we haven't had anywhere near as many cases as some of these models say we would. Well, no, those models were making projections based on the situation back in March, and then March 2020, and since then, we had more social distancing, we had mask wearing, we closed things down, and for sure, there were models that said, well, if you do this and that, then this is what's going to happen. But one hears people talking about, well, we want to do disease forecasts like we do weather forecasts. And of course, there's a big difference. The weather doesn't care less whether I have an umbrella tomorrow. It's not going to stop raining because I take an umbrella to work tomorrow. I mean, I could have done with looking out my window, I could have done with having an umbrella today. But clearly, if you make a disease forecast, people, and people believe it. Of course, not everyone believes them, but some people are going to change their behavior as a result. I mean, and then of course that also then has important implications. I've said this for many epidemics we've had in the past. It makes it very difficult to ask how successful the model predictions have been, because you're always sort of shooting at a moving target, and you can always argue, well, my model was overly pessimistic precisely because you went ahead and did some controls, based on what you saw or based on what my model predicted. So in a way, it's kind of a nice, the disease modelers have always had a nice excuse for why, or the epidemiological modelers have always had that sort of shelter for why maybe their projections are often more pessimistic than what plays out in reality.
So it seems like a next step when biologists talk about phenotypes, then one would partition humans into various behavioral types that respond differently to forecasts. Some don't, some ignore them, some respond in positive, some respond in anti sort of ways. I don't know if you're thinking about that or others.
Well, I don't think about that, but I know there are many people who have been thinking about modeling behavior. So, I mean, one of the places where this has been most well developed has been in terms of vaccination behavior, where, there's like a game theory aspect there between the direct benefit you get, but in some cases, the risk you take by being vaccinated, or the economic, the inconvenience of being vaccinated versus the indirect benefits that you get from other people being vaccinated. So that there's actually quite a well-developed literature on those sort of vaccine type behavior games.
Great, thanks a lot.
But does contact tracing really have anything to do with forecasting future numbers? It doesn't.
No.
That's, I mean, it's
no,
like,
a different. I mean, it's a different.
Right.
I mean, I would not use that model to try and project.
I just was being sure I was deconflicting in my own mind that the contact tracing, I ask you, did you go see these people or where did you go?
Right.
And it's not a behavior that you change after we talk. So, but I would think contact tracing would provide a lot of insight into the R factor.
Right.
Is
Yes.
the R factor what all the other models are assuming? Because if you pick up the data that somebody that was infected had contacts and you contacted them, you are in a better position to say how close were you really,
Right.
and what is the probability of transmission, since we know you were in contact with an infected person.
So contact tracing has provided lots of information on the way that transmission has been playing out, the sort of data that you wouldn't get simply by observing numbers of cases in a population as it spreads.
Now, how does that data get back into the R value computation? Was it used? Or was it ignored?
That is a good question. I mean, I think it has been used. It certainly informed parts of the calculation of of reproduction numbers. I wasn't doing those calculations, so I can't speak for what others did. But for sure, there have been insights into transmission that we've gained. For example, on this question of heterogeneity and super shedders, super spreaders. That become very clear from this sort of contact tracing data, where you can see that some people cause lots of secondary infections and other people cause few secondary infections.
Seems we might have missed some of the best knowledge of contact tracing.
Okay. I think that there was somebody who had their hand up a long time, but they may have dropped off. Other questions? Several of the questions I had lined up were already asked, like microvasculature for Amanda. And I asked, I think, my main question already for Alun. Are there other comments or questions? Greg, you've thought about these issues a lot. Do you have anything you'd like to have clarified?
Well, the one thing I told Alun privately was, why would anyone not have done bidirectional tracing? It's almost insane that you would do unidirectional tracing. And he made the case. Why? Imagine the information that's gained by going back, right? It's just, anyway. I also responded to John. This whole, the way I look at Alun's presentation, what he's done is it's like a piece and the first foundation for a much more general model that one could develop, right? It's the beginning. You could start to add, all kinds of complexities, but we could take hours just to talk about that. But in any kind of, in our big aspiration here to influence funding and directions for funding, how you use tracing and how you communicate the results. I mean, one of my big complaints, I don't think we've talked about this, but in the latest issue, I think it's of Nature, the editor of Nature is Holden Thorpe, who used to be here as our chancellor and a regular faculty member. And his whole point of this recent opinion is the CDC communication to us, right, to the rest of the population. And that's part of what Alun impacts, is just knowing what's the impact of tracing and how could it affect people's behavior, and how does their response to the input they get change, become a feedback loop, right? In my view, this is going off the rails here, but the communication from the CDC we had great aspirations for Rochelle Walensky, but they've been having a hard time walking the tightrope between politics and science and medicine. And it's been very unfortunate. But I think, anyway, just repeating what Alun's presented is the beginning of a way to communicate and to people what the impact is, right, of anything you can do to intervene in a pandemic. So in our big pandemic portfolio, these kinds of models and interfaces with public health is going to be critical.
So because of my sort of path to where I am, it's quite interesting for me to compare the situation in the UK to the US. And in the UK, a lot of the scientific advice comes from academics who are sort of not part of the government. They're on some committee that's convened by the government, but they're not government employees. And so my impression at least is that they're a lot more free to say things and aren't as hamstrung by some of the political conventions and some of the restrictions that sit on federal employees here in agencies like the CDC. I know whenever I'm co-author with as doubtless many of you are, with people from government agencies, papers have to go and get approved and so on. So they're a lot more cautious about their communication, and it has to get approved up and down the chain. And for sure, that makes things more difficult. And of course, back in spring 2020, we had an interesting political situation in this country that made things a lot more difficult.
Also, while the director of the CDC is a political appointment, dealing with the fact that we were learning on the fly. And so you mentioned this, but anything you're predicting in any modeling we do is based on what we knew.
Yes.
Went into the model.
Yes.
And I don't envy I don't envy the CDC director for giving, communicating. But I guess my point is that read that commentary by Holden Thorpe in today's issue. I think it's in Nature.
It's science.
Science, yeah. It's a good comment. Is that, come on, try to do a better job of deciding if your role is pure science or if you're a politician, then be upfront about it. And maybe you ought to not be a politician, I guess, is maybe the punchline of his commentary. But anyway, another couple stimulating talks.
Okay, thank you. Thank you, Greg. Any other questions for our speakers? They both spoke so succinctly. We had more time than usual for questions. Many interesting things brought up.
John put the link to the Holden Thorpe commentary in the chat box. Thanks, John.
Last week we had Philip Ball speaking. And of course, one of the things he was talking about was, he said that he never really believed, as a science journalist, he never really believed that there was a separation between science, politics, and society. But the past year had made that lack of separation much clearer than it might have been otherwise, for both good and bad.
Yeah.
It was interesting. Philip Ball was the moderator for the M-Cell panel on communicating with journalists this afternoon. So I just got to hear him again. And he did the panel that we asked him if he would consider doing for our group.
Well, thanks to our speakers for very stimulating talks. I'm going to be moving on, but I enjoyed both of them. Yeah.
I appreciate that. Thank you all for staying, and I appreciate both of you for coming and speaking to us, and we look forward to talking to you both again.